Acceleration, changes in velocity. Imagine riding in a car. The driver steps on the gas pedal, and the car moves faster. Moving faster means the car's velocity increases. The driver then takes her foot off the pedal, and the car's velocity decreases. Next, the driver turns the steering wheel. The car's velocity changes because its direction changes. The car's velocity changes if either the speed or the direction or the car changes. When a car's velocity changes, the car is accelerating. Accelerating is a measure of the change in velocity during a period of time. An object accelerates when its velocity changes as a result of increasing speed, decreasing speed, or changing speed. You might have experienced a large acceleration if you have ever ridden a roller coaster. Think about all the changes in speed and direction you experience on a roller coaster ride. When you drop down a hill or a roller coaster, you reach a faster speed quickly. The roller coaster is accelerating because its speed is increasing. The roller coaster also accelerates anytime it changes direction. It accelerates again when it slows down and stops at the end of each ride. Each time the velocity of the roller coaster changes, it accelerates, representing acceleration. Like velocity, acceleration has a direction and can be represented by an arrow. Ways an object can accelerate are shown in Figure 13. The length of each blue acceleration arrow indicates the amount of acceleration. An acceleration arrow's direction depends on whether velocity increases or decreases. Changing speed. The car in the top picture of Figure 13 is speeding up. At first, it is moving slowly. Also, the arrow that represents its initial velocity is short. The car's speed increases, so the final velocity arrow is longer. As velocity increases, the car accelerates. Notice that the acceleration arrow points in the same direction as the velocity arrows. The car in the middle picture of Figure 13 is slowing down. At first, it's moving fast, so the arrow is showing its velocity as velocity is long. After the car slows down, the arrow showing its final velocity is shorter. When velocity decreases, acceleration and velocity are in opposite directions. The arrow that represents acceleration is pointing in a different direction opposite to the direction that the car is moving. Changing direction. The car in the bottom picture of Figure 13 has a constant speed, and so the velocity arrow is the same length at each point in turn. But the car's velocity changes because its direction changes. Because velocity changes, the car is accelerating. Notice that direction of the blue acceleration arrows. It might surprise you that the car is accelerating towards the inside of the curve. Recall that acceleration is the change in velocity. If you compare one velocity arrow with the next, you can see that the change is always towards the inside of the curve. Calculating acceleration. Acceleration is a change in velocity divided by the time interval during which the velocity changes. Recall that velocity is the speed of an object in a given direction. However, if an object moves along in a straight line, you can calculate its acceleration without considering the opposite direction. In this lesson, velocity refers to an opposite speed. Positive acceleration can be thought as speeding up in the forward direction. Negative acceleration is slowing down in the forward direction, as well as speeding up in the reverse direction. Acceleration equation. Acceleration equals final speed minus initial speed out of total time. A equals VF minus BI out of t. Acceleration has SI units of meters per second, m/s/s. This can also be written as meters per second squared, meters/seconds squared. Speed time graphs. Recall that you can show an object's speed using a distance time graph. You also can use a speed time graph to show how speed changes over time. Just like our distance time graph, a speed is on vertical axis, the y-axis. The figures on the next few pages compare distance time graphs and speeding time graphs for different types of motion. Objects at rest. An object at rest is not moving, so its speed is always at 0. As this result, the speed time graph for an object is at rest is a horizontal line at y equals 0, as shown in figure 14. Constant speed. Think about a farm machine moving through a field at a constant speed. At every point in time, its speed is the same. If you plot its speed on a speed time graph, the plotted line in horizontal, as shown in figure 15, the speed of the object is represented by the distance of horizontal line is from the x-axis. If the line is further from the x-axis, the object is moving at a faster speed. Speeding up. A plane speeds up as it moves down a runway and takes off. Suppose the speed of the plane increases at a steady rate. If you plot the speed of the plane on the second speed time graph, the line might look like the one in figure 16. The line of the speed time graph is closer to the x-axis at the beginning of time period when the plane has a lower speed. It slants upward towards the right side of the graph as its speed increases. Slowing down. The speed time graph in figure 17 shows the motion of a space shuttle just after it lands. It slows down a steady rate and then stops. Initially, the shuttle is moving at a high speed at a point representing this speed is far from the x-axis. As the shuttle's speed decreases, the points representing its speed are closer to the x-axis. The line of the speed time graph slopes downwards to the right. When the line touches the x-axis, the speed is 0 and the shuttle is stopped. Limits of speed time graphs. You have read the distance time graphs show the speed of an object. However, they do not have described the description in which an object is moving. In the same way, time graphs show only the relationships between speed and time. A speed time graph of the skier in figure 18 would show changes in his speed. It would not show what happens when the skier's velocity changes as the result of a change in his direction. Summarizing motion. Now that you know about motion, how might you describe a walk down the hallway at school? You can describe your position by the direction and distance from a reference point. You can compare your distance and your displacement and find your average speed. You know that you have an instantaneous speed and can tell when you walk at a constant speed. You can describe your velocity by the speed and your direction. You know you are accelerating if your velocity is changing.